Hello students, in the previous lecture we discussed about Biot-Savart's law where you could calculate the magnetic field B due to steady currents. There as an example I also showed you what will be the magnetic field of a straight line current. So that turned out to be mu 0 I by 2 pi s, right, if you remember. Now let's begin this lecture by calculating the divergence and the curl of B. Now looking at the magnetic field B from your previous examples, you could clearly figure out that it has a non-zero curl. But let's just see for a simple case of a straight line current, what is the curl of this field. So let's imagine a straight line, a straight wire carrying a current I along this direction. And then the magnetic field, as you have previously calculated, will be like this line, circles circumferencing the wire. Okay, so now imagine if you want to do a line integral of this magnetic field along this path, so that will turn out to be B dot dl, and that will turn out mu 0 I by 2 pi s dl, and then B is uniform along this path, so that you can take out mu 0 by 2 pi s outside and then do the integration only for the dl, and that turns out to be, so the dl integration will give you s 2 pi s. Okay, so the 2 pi s cancels out, and that you finally have to mu 0 I. So what you see here is that this B dot dl integration is independent of s. So if you are doing for this particular loop, we are doing an integration at distance s. Now it doesn't matter where you are. I mean, it will be independent of s. That's because of the fact that as you increase this s, B decreases. Okay. At the same time, so that way the line integral remains constant. And it's also true for any closed path, and that you can figure out by doing the same integration in let's say cylindrical coordinates by expressing dl, like you can check it, so please verify it. So you can take the dl as ds s cap plus s d phi cap plus d z cap, right? So you do that and then do the integration, and then as you know, the magnetic field direction is around phi. So you will end up this integration as, so this integration will come out to be mu 0 I by 2 pi, and then integration 0 to 2 pi d phi. Okay, so that will again give rise to mu 0 I. So what it tells you that if you have a loop and that encloses some current I, so your B dot dl will in general give you mu 0 and whatever current it encloses. So you have, let's say, one wire or two wire having current I1 and I2. So this, if you are encircling both the wires, you will have the total current enclosed. But if the wire is outside the loop, okay, so then this d phi integration will yield you 0. Okay. Okay, so because this will not enclose it, and then you will in general you can write that B dot dl as mu 0 I enclosed. So with that, and as I told you, this also true for non-circular path as well. So so it's a more general theorem that your I enclosed, sorry, B dot dl is mu 0 I enclosed. However, what is I enclosed? So I enclosed is nothing but the total current enclosed by the path, and that's in terms of current density, you should be able to figure out that the I enclosed is nothing but J dot dA. Okay, that's J is your current density, right? So now your I enclosed is nothing but B dot dl, and your and then you can write that nothing but mu 0 J dot dA. Same thing. Then you use your Stokes theorem and you convert this B dot dl into your del cross B dA, and then both to make it both area integration, and then from that you can obtain this particular general formula, that del cross B equal to mu 0 J. Okay. So that is for a infinitely long straight line current. Right, because if you remember the expression for magnetic field B as mu 0 I 2 pi s you got previously for a infinite straight wire. Okay, so the assumption here we had is that there is a infinite straight wire, and but if you want to really calculate for a general case, because not all currents will be in this form, right? So if you want to calculate the divergence and the curl of B for any general current, then you have to use the expression as you got from Biot-Savart's law. Okay, like this expression. Okay, so you just take this expression and then calculate the both divergence as well as the curl. Now, before you do that, please remember B is a function of R, so that way it is function of X, Y, and Z. Your current density J, so that is a primed coordinate, so that will be function of so your J is a function of X prime, Y prime, and Z prime, and your the curly R is nothing but X minus X prime X cap, Y minus Y prime Y cap, Z minus Z prime Z cap. So that's my configuration. Okay, so now with this set of problem, now what you can do is that you then calculate del dot B, so that the divergence of B. So take this expression, and then if you do the divergence, so as it turns out, this is del dot a cross product of two vectors, so that you can use your product rule, and that turns out to be r cap by r square del cross J minus J del cross r by r square. Now this is 0. Okay, that's purely because of the fact that J is a function of X prime, Y prime, and Z prime. So this will inherently give 0. And this one you can show, I mean, that's the exercise for you. You can show that this is also 0. So both terms being 0 means that divergence of B is 0. And that's true for any current. Okay. So remember this. Now what it turns out that divergence of B is 0, or B is divergenceless. What about the curl? So now you got the divergence of 0. So now the question is, what is del cross B? So you use the same expression for Biot-Savart's law, what you have obtained, and then to take the del cross of that, del cross B. So del cross B will turn out to be a del cross J cross R by R cap by R square d tau, and then you can use the product rule. So the product rule you can verify for such an expression, it will come out to be this. Here you can safely take out or eliminate the derivative of the J, because J is a function of prime coordinates. So your derivative with respect to normal coordinates like X, Y, Z will yield 0. And then if you get rid of those terms, the derivative terms, you only have these two terms. The second term is 0. Again, that you have to verify yourself, that the second term, this I don't know why, yeah. So the second term is 0. That's again a task for you. Please do that. Okay, so this one you verify. Okay, and this one you have already done as an exercise some point when you were doing the vector algebra, and that turns out to be 4 pi the delta QR. Okay, so then eventually what it gives you, that del cross B, the curl of B, is nothing but mu 0 by 2 pi, mu 0 by 4 pi, J r prime 4 pi del Q r minus r prime, because your curly r is nothing but r minus r prime. So using the property of the delta function, okay, you can show that this will now give del cross B as mu 0 J r. So please remember this very So the divergence of B is 0. Curl of B is nothing but mu 0 multiplied by the current density. Okay, so now this is a very famous law. So that is known as Ampere's law. So what you have obtained, the curl of B as mu 0 j is known as Ampere's law. And that's in differential form, of course. So you can convert it into integral form by using Stokes' law. So your del cross B, if you take an area integration of del cross B, that should be B dot dl, and you know that B dot, and that is nothing but your, so you take the area integration of both sides. So the right hand should be mu 0 j dot dA, and your left hand side you can make it a line integration of B dot dl. So you get both the terms, and then you eventually find out that B dot dl is mu 0 I enclosed. So that's the integral form of Stokes' law. Sorry, Ampere's law. Okay. So Ampere's law is very important law in magnetostatic because it allows you to calculate B wherever symmetry allows you. Okay, if you are provided with an appropriate symmetry, you can calculate B using Ampere's law very easily. So, what do I mean by that? So imagine you have a symmetry where you can take out B outside the integral, and then all you have to do is just a DL integration. So that makes the job easier. And so there are some particular symmetries which allow such kind of operation, that taking B out of the integral and doing the DL integration. And those in those kind of symmetries only you can use Ampere's law and calculate easily the magnetic field. And it turns out that you can use it in the following scenarios. If you have either an infinite straight line, straight wire, or you have an infinite plane, or you have infinite solenoid, or a toroid. So we'll take a couple of examples, particularly for the straight line. The rest of the things probably you can take as an assignment and see how Ampere's law helps you to calculate the magnetic field B. So let me just give you some, first start with a very simple example, which you have already done using Biot-Savart's law. So let me just take a straight wire with a current flowing like that. Okay. So the current is flowing like that. Now, if I want to calculate magnetic field B at a distance S. So what you do, then you create an Ampere loop at a distance S, which is like a circle with the wire at the center at distance S. So the radius now is S. So now B will be uniform. So the thing is that B will be uniform along this loop. In that case, your B dot dl, as you know, since the circle encloses the current, so your B dot dl will be mu 0 I enclosed. And since B is uniform, you take the B out of the integral and you only do the DL integration, and DL integration is nothing but the circumference of this loop, and that is nothing but 2 pi s. So your B into 2 pi s is nothing but mu 0 I, because current enclosed is nothing but I. There is only one wire with a current I, so it is mu 0 I. And so if you just do some little algebra, you will eventually end up with the P is mu 0 I by 2 pi s. This is the same result which you obtained previously using other methods. Okay, but as you see here, the mathematics is very simple. Okay, you do very simple mathematics to calculate B for. And one thing again, I should emphasize that here the symmetry allows you to calculate B using Ampere's law. And that's the vectorial form where B is along the phi cap. That anyway, you have already done this example. Now let me make it a little more complicated. Okay. And then let me taking instead of a wire, let me take a cylinder. Okay. And then ask what is B if you are inside the cylinder or if you are outside the cylinder. And then I can also make it conditional, saying that I is uniformly distributed on the surface, then what will be inside? Okay, if your I is only distributed on the surface, now the question is what will be the B inside and outside? And if instead of I being a constant, the instead of J being a constant, I can also make a point, make a condition that your current density is proportional to S. So where the S is the distance from the center. Then there are these two conditions, and I want to calculate B in these two conditions. The first condition is very easy. You know that I is distributed on only the surface. So if you are inside the cylinder, then what is the current enclosed is 0 because I is only on the surface. So your B dot dl, as you know, is nothing but mu 0 I enclosed. So then it makes very easy. So if you are outside this cylinder, your current enclosed is still I. And but if you are inside the cylinder, where your distance S is less than A, then what happens is that you don't enclose any current. So your current enclosed is 0. So, so that's what will happen. So B dot 2 pi S, your B dot dl is nothing but B dot 2 pi S. S can be inside or outside. Okay, this S can be less than A or greater than A. Now, depending upon if it is less than A, which means you don't enclose a current, so your B is 0. But if S is greater than A, you enclose the current I, so your B is mu 0 I by 2 pi S. The same result as you obtained before. Okay, for a wire. You see how easy it is to use Ampere's law and calculate magnetic field. Now take the second case where I say that your J is proportional to S. Now here I have a condition that the current density is proportional to the distance from the center. Okay. And in that case, let's just say that J is Ks, where K is a proportionality constant, some constant. Then our first job is to calculate what is I. Okay. And you know J dot dA. If you integrate it over 0 to A, then you get the total current I. So your J is now Ks and dA is nothing but 2 pi S ds. So how do you get that? So you have you take a kind of a thin shell and then your S, this is your S, and that's your ds. So then the area of this particular shell or the will be nothing but your what? 2 pi S ds. Okay. Now this one you integrate from 0 to A. And J is nothing but Ks. So if you do all the algebra, you say you end up, you calculate the proportionality constant K as 3I by 2 pi AQ. Now the job is simple. All you have to do is that B dot dl as mu 0 I enclosed and B dot dl you know. Only thing you have to calculate I enclosed. So if you are outside, I enclosed is still I, right? Because your total current is I. So your B dot 2 pi S is mu 0 I, and then it turns out to be the same result as before. But if you are inside the cylinder where S is less than A, then the situation is different. Now your, depending upon where you are, your total current enclosed will vary. Okay. So because of the fact that your current density is proportional to the distance from the center. And for that reason, if you are at distance S, which is less than A, your B dot 2 pi S will be nothing but I dot I enclosed, and to calculate that, you have to do the integration of J dot dA until that point. Okay. And again, you follow the familiar algebra, and then that is K S 2 pi S ds, and you now you know the value of K. And if you do that, you will eventually end up B as mu 0 I by 2 pi AQ multiplied by S square. So in summary, you can write that B outside is same result mu 0 I by 2 pi S phi cap, whereas inside it will depend where you are. It turns out that it is mu 0 I S square by 2 pi AQ phi cap. Okay, so I just took two examples and showed you how Ampere's law can help you to calculate the magnetic field. And that is, these two examples are from the straight line symmetry. So we'll try to give you some assignment problem where you have, other than the straight line symmetry, you have other like infinite plane or infinite solenoid. And then you can also see Griffith's many examples where it has taken different examples for these different symmetries, and then it has calculated the magnetic field B. Okay, so please see that and then try to look at different problems on Ampere's law. If you have any issue, we can discuss it more on the live sessions. Okay, thank you.